from NASA's Goddard Space Flight Center in the US. So Jane earned her PhD from the University of Arizona, where she worked with George Rigby on observations of AGN over a broad range of wavelengths from the infrared to the X-ray. From there, she moved to the Carnegie Observatories in Pasadena as both a Spitzer Fellow and a Carnegie Fellow before joining the staff at Goddard, where she is now. She originally joined the staff as a Deputy Operations Project Scientist for James Webb Space Telescope, and she's now a Project Scientist for Operations for JWST. So in addition to winning lots of awards over the years and having a really great TED Talk that you can watch on YouTube that I highly recommend, Jane has extensive experience using NASA's great observatories, so Hubble, Chandra, Spitzer, as well as many of the largest ground-based telescopes in the world, like Keck, Gemini, and Magellan. She's a member of the Science and Technology Definition Team for LUVOIR, so she's already thinking about kind of next generation optical and UV astronomy. But soon she'll be using the James Webb Space Telescope to push the frontier in the near infrared. She's the PI of an early release science program targeting extremely magnified lens darks in their star formation. And so today she's going to tell us all about using gravitational lenses to dissect galaxies. So take it away, Jane.
Great. Thank you, Jordan. Can you hear me okay?
Yes.
Good. And thank you all for being here, especially I know today is this is the week of the Hubble proposal deadline. Trust me, when I reserved this time slot a long time ago, the call had not even come out. And in fact, I'm sorry I have to join you virtually. I deferred this talk at least once, hoping that we could get through the pandemic and I could go visit in person. And here we are a year later, and we're all in our rec rooms. So I'm sorry I can't be in your lovely city in person. We'll just have to take a rain check on that. And when it's all over, you can come visit Goddard as well. So I want to, so yes, please ask questions, because otherwise it's just me talking to myself in my guest room. And those of you who are professors have a lot more experience talking to black little rectangles than I do as part of your day job. So we'll see how this goes. Ask lots of questions so that I get to think new thoughts. So in this talk, I want to talk about the power of gravitational lensing to understand galaxy evolution. And I'm going to start with some big picture science questions. In part, I gave this talk at Stockholm, at the Stockholm University about a month ago, and I brought, well, the entire Swedish internet failed while I was giving my talk, so I blame me. So if that happens, really, Montreal, I'm sorry. So they asked me to spend some time on really big picture stuff. You know, where is the field of galaxy evolution going? Where has it been and where is it going over the next 10, 20 years? So I'll do that with some motivating science questions. I'll talk about 3 tools to address those science questions. And then I'm going to pivot to showing you some examples to prove the point that lens galaxies, at least the brightest and most highly magnified, are really spectacular ways to do things that are otherwise illegal. In terms of understanding galaxies and galaxy evolution. I will then do a somewhat bang, bang, bang science results with citations to papers that you can go read if you're really interested, and then talk a little bit, if there's time, about the future, particularly with the Webb telescope, which will be launching late this year in 2021, and LUVOIR, which is a mission concept for a large UV optical infrared telescope that was submitted to the US Decadal Survey. There we go. So I want to first acknowledge fantastic collaborators, and I'll be showing off results of a number of the postdocs and graduate students within our team, and just say that, you know, working with great collaborators isn't why I got into science, but it's why I stayed. In particular, I'll show some results. The top line here is the faculty types of us who've been, I'm not sure leading is the right word, but shepherding the SGAS collaboration, and then a number of grad students, postdocs, and postdocs who then turned into faculty members who've written a lot of the papers that I'll talk about today. In particular, I want to highlight Michael Florian, who's, go back, former postdoc with me at Goddard, and then Ramesh Manali and Sonia Sharma, who are current postdocs working with me at Goddard. And then John Chisholm, who has worked with me as a postdoc and is now new faculty at UT Austin, and Gaurav Kuller, who's a graduate student finishing up at the University of Chicago, and just won a JWST program as principal investigator that I'll talk a little bit about. All right, so let's dive. Oh, and then I should mention also Emil Rivera Thorson. I'll show some of his results for the sunburst arc, and Ayan Anchara, who was a graduate student at Australian National University working with Lisa Keeley, that we wrote a couple papers together. All right, so let's dive into this. So I put together the sort of big picture. Why are we doing this? Where are we trying to go with galaxy formation in a question? And so I would frame that question this way. We want to know, how did galaxies form after the Big Bang? How did they grow through galaxy mergers and gas accretion? How did they turn their gas into stars and heavy elements and grow their central supermassive black holes? And then through those processes, drive gas out into the intergalactic void to either hinder or further future episodes of star formation. And it really is amazing how much progress we've made on understanding, we now know, it's now a solved question, when galaxies form their stars. We know that through deep field surveys with the Hubble Space Telescope and the Spitzer Space Telescope. We now have a really gorgeous picture of when the stars formed over cosmic time and how the stars, the stellar mass, built up over cosmic time. And it's lovely that those numbers even agree. And so we know that when we look back into the distant universe, and as we look ahead to, say, the era of reionization as captured by the Webb telescope and other surveys, we're really looking at this era of redshifts of 8 to 10 on the right side of the left diagram here, which are, the 500 million years after the Big Bang, where galaxy evolution really gets kicked off. And that's really where the frontier is. It's where we're most ignorant. And on the right side, you can see that that amounts to a very small number in terms of cumulative stellar mass density, right? Almost no stars that are still here today formed at that epoch, but it's where all the action gets started. I spend a lot of my time working on this sort of broad hump here from redshifts of 1 to 4, when half of the stars that ever formed, and where the star formation density was 100 times higher than it is today. And so, it's easy to study star formation at redshift 0, but the physical conditions are very different than they were back at redshifts of 2 to 4. There's just the star formation itself is happening in a much less vigorous fashion. It's a party that's basically done at redshift 0. Right, and so there's a ton to do in this intermediate redshift zone, which covers most of cosmic time, and then at very high redshift. And so some big open questions that we're trying to solve here. How universal are the processes of star formation over cosmic time? We use local analogs, the Magellanic Clouds, our own galaxy, other nearby galaxies as analogs for understanding star formation in the distant universe. But we still really don't know how universal are those processes. We know that the physical conditions were quite different, and so one could expect that the processes differ as well. We really don't know that well how different were galaxies out 7 to 13 billion years ago from galaxies today in terms of their physical conditions. We still don't know. We have strong suspicions, but we really don't know how the universe was reionized and which galaxies are to blame in the few 100 million years after the Big Bang. That's very much a JWST problem. We don't know whether star formation is self-regulating, whether the feedback of star formation, of the outflows of gas, regulate the amount of future star formation. And we don't know whether that causes scaling relations. It's nice to blame scaling relations on those regulatory processes if that's actually what happens. We don't understand very well the massive stellar content of galaxies outside the very, very local universe, Magellanic Clouds. And we don't understand how that stellar content may be different than in the Magellanic Clouds and what the impact is on their host galaxies. The most massive stars, of course, are the ones that go supernovae, the ones that make the heavier elements, and the ones that drive both the stellar winds and then the supernova winds. So they also make all the ionizing photons, and so they're really important and have been very hard to study. And I'll show some examples of how we can study them. We don't have a great handle on how gas flows out of galaxies and what the impact is of that. And we don't, from sort of a technique standpoint, we don't know that well how different are the physical conditions inside distant star-forming galaxies compared to those today. And we can get into knots about which diagnostics of those physical conditions are reliable and which are have systematics that haven't been properly dealt with, in part due to the fact that the physical conditions are quite different. The diagnostics can run astray. So I'll talk a little bit about that later. So let's switch here and talk about tools to address those big science questions. And those are just 3 basic tools. The one I don't need to tell you is that telescopes are time machines. Boy, is that handy. It didn't need to be true that we could see out 13 billion years into the past, but it is. The second tool is cosmic telescopes. It didn't have to be the case that the universe provided us with beautiful, massive galaxy clusters that act like lenses for background galaxies. It's so convenient that that's the way GR works out, that in rare cases, galaxy clusters can magnify the images of background galaxies by factors of 20, 30, even more. And so stretching them so they're much bigger, so we have access to greater spatial resolution than we deserve, given the diffraction limit of our telescopes, and just making them brighter so we can get more photons into our light buckets. And so that's really convenient. You can look at beautiful pictures, like this is Abell 370 from the Hubble Frontier Fields, and basically everything blue in this image is a lens galaxy. Almost everything in this image is a lens galaxy, and you can even see the cosmic shear. You can see that it looks like someone smeared the image in a circular way. That's the lensing right there. But what I'm going to talk about mostly in this talk are galaxies like this giant arc in the bottom of the image that have been magnified by factors of 20 or 30. And so those are the cases where we can do really transformative stuff. And so, what's transformative about that? This is an example from a series of papers I did with a graduate student, Tracy Johnson from the University of Michigan. On the left in blue is what this lens galaxy at redshift 2.5 looks like to Hubble. And in gray in the center here is our reconstructed image through the lens model. You can just ray trace the cluster. That's the beautiful thing. You can map out where the mass of the cluster is from where the galaxies are, throw in some dark matter, and you can make a cluster model that makes very testable predictions for the multiple images. Every multiple image of the lens galaxy has got to give you the same reconstruction in the source plane as you ray trace it back. So this is that reconstruction in the source plane, what that galaxy would look like were it not lensed. And what we found in Tracy's work is about 24 knots of star formation. This thing is just popcorn all over, forming stars in these little knots that in the right here is showing what that galaxy would look like were it not lensed, but were just a deep field galaxy to both Hubble on the left panel and Webb to the right. And you can see that you miss all of that star formation. All you see is an extended disk. And in fact, what you see is a very smooth exponential disk that looks very uniform, but in fact, it's fireworks all over. You just lacked the spatial resolution. So the two things that lensing buys are both just raw brightness. Lens galaxies are brighter, and so you can pack more light down the slit, and then the spatial resolution. And as I'll talk about as we move into the Webb era, where the sensitivity is 100 times greater than we've ever had, then I would argue the raw sensitivity is less important because Webb is able to get some of these line fluxes for unlensed galaxies. But then what is really critical is the spatial resolution. Because without lensing, the spatial scales that we're probing here are on these left panels is about 1 kiloparsec, or maybe, in the bluest bands of Hubble and Webb, if it, looks really good at 1 microns, is, 300, 200 parsecs. Those really aren't the scales that we want to be probing when we're talking about galaxy evolution. We want to be on scales of tens of parsecs, which are the scales at which star clusters form, and are the scales that are accessible with lensing. All right, so third tool, diagnostic spectroscopy. This is from a paper by Max Bettini in 2000. It's the first really gorgeous spectrum of a lensed galaxy at CB58 at redshift 2.7. And this was a really inspirational paper for me as a graduate student. And then as a postdoc, because it was a chance to see what galaxies look like in really high definition. And in fact, all of these little bumps and wiggles in the spectrum, they aren't noise. They're the sums of stellar photospheres of the massive stars that make up the stellar continuum. So pretty much every little blip here is real, and it's it's little features of metals. And you also see in pink shaded are faint emission lines. The spectra are riddled with these little faint emission lines that tell you about the physical properties of the nebulae. And in blue are faint signatures of the hot stars. So you see it right, there's carbon-4 at 1550 angstroms. That's a big stellar wind line that's driven by the massive stars. But there are also all these lethal absorption features that are photospheric absorption features of massive O and B stars that tell you, as I'll show later, what are the stellar populations inside of that galaxy. And so for a long time, this spectrum and this galaxy was an army of one. It was the only one we knew about that was this bright. And as I'll show, we now have a sample of about 20-something galaxies that are this bright, where we have spectra of this quality published.
So
and in fact,
can we pause there to address a few questions before you move on?
Sure, absolutely, great.
Daniele, do you want to unmute yourself? See yours first.
Yeah, sure. I guess you already answered a bit during while speaking, but at the beginning you had all these questions. I was wondering what is the relevant redshift to consider for to answer these questions on galaxy evolution?
And look at the sort of what are the big questions here in terms of redshift. I would say that for the first one, what is the impact of massive stars? It's at any redshift where we can make the measurement. It is such a pain to really measure massive stars. And so I would say that that's a challenge to get at any redshift. Gas flow, I think that that's one where you need good sampling over redshift, just because the IGM has changed so much over cosmic time. And for the physical conditions, in my head, I have that broken down into about 3 categories, sort of today, cosmic noon, redshifts 1 to 3, and then way out there, the epoch of reionization of sort of 9 to 10. And so I would say that's true for most of these questions today, that it's really about the baby pictures of the universe, the adolescence, and then it's, I don't know what we want to, how old we want to say the universe is, but it's semi-retirement today.
Okay, great. And Vicky, did you want to ask your question as well?
Okay, yeah, it was when you were talking about the reconstruction of the lenses. So I had 2 questions. One is, you said, oh, throw a little dark matter in. And I just wondered, it must depend somewhat on the model for dark matter. Like if the model were super clumpy, maybe that could change, where you could reconstruct clumps. And then my next question was, are there any cases where the actual, or separately an actual image of the same field has sufficient angular resolution that you could actually check your reconstructed image and know you did it right? So
yes and yes. For some of the examples I'll show, we have 3 or 4 good there are 3 or 4 multiple images. And yes, you can reconstruct ray trace each one back and compare them. And that gives you a good estimate of the robustness of the model. It's generally pretty good. The way the lens modeling works, so you have, you're using families of multiple images as constraints. And then you use the redshifts use the dispersion of the cluster, which tells you something about how big about the total mass. You also use the positions of all the light, right? So all of the cluster galaxies. And if you're not sure, you measure redshift, so you know it's at a cluster galaxy. But the fact that they have a color sequence makes that easier. And then you add a uniform halo, or in some cases more than one halo, depending on how relaxed or perturbed the cluster is. You are totally right that if dark matter has clumps, and particularly clumps that don't have luminous counterparts, then you ought to see substructure in the lensing that doesn't show, that you can't explain by the luminous halos that you see. And totally, that is a game that people play. Absolutely. And I should mention that for our team, our expert on that is Karen Sharon and her postdoc, now former postdoc, Guillaume Mahler. And this is a total kind of dark art of doing the lens modeling. And it always freaks people out. This is always like the first question in a colloquium is, well, how do you know that the reconstruction is robust? And I'll show you an example where we have 11 distinct images of the same lensed thing. It's the same star forming region. And it pops up 11 times through this lens galaxy. And so you need a model that can explain all 11 of them. In general, it works really well. And one of the reasons that Karen is a wizard is that you get a good sense of whether the reconstruction is robust, the lens model is over-constrained or under-constrained. Basically, did nature give you enough enough galaxies behind the cluster such that you have a lot of lens galaxies to act as your constraints? And so the ones we end up tossing from our samples, it's not that we can't make sense of the lens model, it's that there just aren't enough constraints to make a lens model.
Okay, thank you.
Great, we're all caught up. So thanks for letting us pause there and do continue.
Rehydrate and move on. All right, so, okay, so diagnostic spectroscopy, really powerful. This is the rest frame ultraviolet. Can you stop spotlighting me? Is that a thing that is possible? Remove spotlight. Well, there we go. So it is a weird thing about, paradoxically, it is easier to get spectra like this out at redshift 2.7 than it has been to get them for galaxies in our own backyard. And the reason is that UV photons are a lot harder to detect than optical photons, and factors of 30 or 40 of lensing magnification are really helpful. And so paradoxically, you know, these sorts of spectra have been available at redshift 2.7 since 2000, but only with the installation of the COST spectrograph on Hubble in 2009 did it become possible for nearby galaxies. And so we now are at a fortunate place where we can get rest frame ultraviolet spectra for nearby galaxies, like these examples, and matched in terms of data quality out at redshifts of 2 to 3. And I mean matched in terms of signal to noise per spatial resolution element. So we can really do apples to apples comparisons of the stellar content and the outflows between low and moderate redshift. And just to say that there's a lot of other spectral diagnostics in the rest frame optical, and this is and that's something that, you know, there's a reason that both it's easy to study the rest frame optical and there are very powerful spectral diagnostics. And so that's something that Webb will be doing a lot, is rest frame optical spectroscopy of galaxies redshifted out into the near and mid infrared. Okay, so I want to give you some examples to show that this is real, and I'm not just making this up, of how powerful these techniques can be to study galaxies. So, and I want to just back up and say that when I'm talking, the samples that I'm talking about are drawn from large area surveys of most of the deep extragalactic sky. So they're not drawn from, say, the Abell clusters of, you know, the most famous clusters that folks have known about since the days of photographic plates. These are systematic surveys of Sloan and now other surveys like DECALS looking for really bright arcs. These are some of the, so that's the SGAS survey led by Mike Gladders out at the University of Chicago. This forms the basis for a lot of what I'll talk about here. And for these kinds of surveys, you don't find the most massive clusters. You find the best lensed galaxies, right? Because you could have a really massive cluster, but then nothing behind it. It just has nothing to lens, so you don't get giant arcs. These SGAS lens galaxies here, these are not Hubble images. This is 5-minute pre-imaging with Gemini. So very shallow imaging, and the arcs pop up, right? So the typical magnitudes for these things, if you think in magnitudes, are in the 20, 21, 20 and a half, and that as composed, so that's about 100, that's 70 times brighter than the field counterparts, and so it really enables some transformative spectroscopy. And so that's what I've been doing, is going after these targets where they're just so bright that we can do kinds of spectroscopy that without lensing are just totally not possible. So here's an example of that. This is RCSO 327 at redshift 1.7. And this thing is spread out over 38 arc seconds on the sky, such that as where the arrows are, we've gotten spectra of different parts of the arc, and now have put integral field units on top of this thing. And so we can see how much the galaxy varies spatially and study pieces of star formation that are only 30 to 50 parsecs. And so in fact, this is the lensing reconstruction of this galaxy. And to Vicky's point, if you go back to the Sharon et al. Paper, there are reconstructions of all 4 images that we see, and the reconstructions all look really similar. So that builds a lot of confidence that yes, it's a robust model. And you can see circled here where these knots, where the regions with arrows, where they correspond to in the source plane. And in fact, from velocity maps with the OSIRIS instrument on Keck, we know that this is a major merger in process. And so you have this tidal tail in red falling behind, and you have a major merger between a gas-rich galaxy at left and a gas-poor galaxy at right. We also find things like this fantastic object, which is a lens galaxy at redshift 5.0 that is very bright, Z magnitude of 20.5, that was discovered by Mike Gladders and his undergraduates. He did one of these, learn how to observe classes for undergraduates, and so he gave them a real task of analyzing deep imaging data and finding these lens galaxies. And so this was the first of their discoveries. They have a couple other papers in preparation. This is the brightest redshift 5 galaxy that we know of. So it's really the post-reionization epoch. The brightest galaxy we know that we can study in the post-ionization reionization epoch. And so Gaurav Kular, who was the author of the discovery paper on this, just had a successful JWST proposal to follow this galaxy up in cycle 1. So that's exciting, especially because it's led by a graduate student. And there are more of these types of galaxies to follow. One of the goals of Cool Lamps is to find a bunch more of these high redshift, very bright lens galaxies, because there are a dearth of redshift 3 to 5 lens galaxies for observational selection reasons. And even, I'm going to mostly focus on optical IR and UV techniques, but with lensed samples, this is a lens galaxy where in the X-ray you can see a strong detection of what turns out to be X-rays from X-ray binaries within this galaxy. So it's not an AGN. You're seeing, we think, the X-ray emission from the massive stellar populations. And this just shows kind of what that looks like in the deep fields, where the black line is how well Chandra can do in the deep fields. And you can see that that for this lens dark, it's a really easy target apparently, but then the intrinsic luminosity that you're probing down to is really much better than we can do with current telescopes. So that's neat. Okay, so now let's dig into some science results. I want to talk a little bit about the Megasaurus survey, and then I'll show you some results from Megasaura and from its allies. So Megasaura was a program that we started back in 2010 to obtain gorgeous rest frame UV spectroscopy of the brightest lens galaxies that we could find. And so the sample paper for that is in Rigby 2018. We have an extension to it that we're writing up now. The total is 20 very bright lens galaxies with really high quality spectra. And so by high quality, I mean spectral resolution of about 3,300 and signal to noise of 20 to 40 per resolution element. So that is matched to the best spectra from COS at redshift 0 to 0.3. And these will always be the brightest lens galaxies that are known. These will always be the best targets for this and other kinds of work because they were found by searching most of the sky. So, at best there's another factor of maybe 2 or 3 more out there. But these really are the brightest galaxies that we'll always have at our disposal to push our current telescopes further. So let me show you some results from that survey, and we have a logo made by a 7-year-old. of a dinosaur. So these are some of the spectra. If you're used to ultraviolet spectroscopy, I'll give you a moment to love them. If you're not, I'll tell you that these are just really great spectra, very high quality and relatively high moderate spectral resolution. And so just zooming in on one of those, you can see a tremendous, that's just one spectrum in echelette, multiple panels. There are multiple diagnostics here of the emission lines from the nebulae, absorption lines from the stellar winds and the gas flowing out of this galaxy, and then faint photospheric lines from the massive stars. Right, so there's just a tremendous amount we can do with data of this quality. The whole point of taking data of this quality was so that we didn't have to deal with stacks. We could deal with individual galaxies and not deal with the difficulty that when you stack a heterogeneous sample, you can really get confused as to what you're seeing. But I stacked it anyway because I thought it would be useful for people. So if you want a template in the rest frame UV, I would encourage you to use ours from 2018 because it is higher signal to noise and higher spectral resolution than the previous, and larger wavelength coverage than the previous templates that people have used. But I don't want to, all right. And you can just see that at that higher resolution in black here, you're picking out a bunch of these absorption features of the massive stars that we use to date the stellar population. And we're grateful to Time from multiple institutions to do this work. Let me show you some science results. So physical conditions. I'm going to go a little bit fast here and just say that in a number of papers, we've been working to understand what are the physical conditions inside redshift 2 to 3 star-forming galaxies, how much have they evolved from redshift 0 samples, and are we measuring what we think we're measuring? Do we understand the diagnostics? And so in the paper by Anna and Shara, 2019, and then my paper from this year, we just made plots of what are all the diagnostics of a given measurable that we can make, and how badly do they disagree? And so in the bottom left, you can see a bunch of different ways to measure metallicity, oxygen to hydrogen abundance. And there are significant offsets at the half-a-dex level, so a factor of 3, between these techniques. And those aren't measurement error, those are real systematic differences in the techniques. Similarly, in the middle panels, if you're trying to measure a pressure or a density, what technique you use gives you a really substantial offset, almost 2 orders of magnitude in the measurement, and that's real. You're sampling different regions of the nebulae, hotter and denser versus cooler and less dense. And so, we put out some best practices, but one of the things we point out in this paper is that if all you have are the UV diagnostics, you can really fool yourself because you're seeing denser regions of the galaxy. That when you have optical data, it is much less extreme. So in this middle panel here, this is a UV diagnostic versus an optical diagnostic. And so for folks using these diagnostics at high redshift, where all they may have is the UV, you can fool yourself into thinking the galaxies are much more extreme than they are because you're looking at the most extreme region. So we really geek out about these diagnostics, but in that series of papers. But here I just want to say that that's one of the things we're doing, is understanding which by using lens galaxies where we have signal to noise to burn, understanding which diagnostics we should trust for larger samples of unlensed galaxies. All right, I want to talk about ionizing radiation because it's really cool and it's of a lot of interest to folks thinking about how we went from a neutral universe that cooled after the Big Bang to the ionized universe that we know and love today. This is my current favorite galaxy in the whole universe, the sunburst arc at redshift 2.3. It is just an incredibly cool galaxy. Let's take a look. So I don't have a zoom in on this. Okay, so what you see is 3 big images here. The thing is huge. It's so bright that its brighter star-forming regions are misclassified as USNO astrometric stars in the USNO atlas. Like they're 17th. It's just, the thing is so bright. And so we got a spectrum of this with Magellan, and we saw that the Lyman alpha had these 3 peaks, a red, a blue, and then a central peak. And I remember sending some emails to folks saying, I don't know, what is that? I don't know what it is. And then I had one of my better ideas, which is that I sent it around to some new postdocs that folks knew, and got back from Emil Rivera Thorsen this like really long email explaining that this was actually a prediction from theoretical models and that it was really cool because what you were doing is you were seeing straight into the galaxy along a channel that has no gas in the way. And so you're seeing Lyman alpha escaping without scattering at the systemic redshift, as well as the scattering wings to the blue and red. And we said, okay, that's cool. And then in that paper, we predicted that if that's true, you should see Lyman Continuum streaming out as well. Ionizing photons. Sorry, Lyman Continuum is, I don't know why we call it that, but it's photons that can ionize hydrogen. I mean, I know why we call it that, but it's just sort of jargon. We should see ionizing photons streaming out. So we went and looked. So we got Hubble data. This is what this thing looks like. These blue knots are actually the same star forming region seen 11 times in total. It just keeps popping up because of the lensing geometry of this thing. And this is this ionizing knot that is not so much leaking ionizing photons as spewing them out. Over here on the right, this is from Emil's paper in Science from 2019, is the ionizing continuum. So this is ionizing radiation, and you can see the rest of the galaxy just drops out. And then this bright region seen multiple times is just spewing out something like half of all its ionizing photons. So this is the best example that we have of how galaxies can manufacture ionizing photons and then get them to escape as is needed to keep the universe ionized and to reionize the universe. But it's been really hard to find examples of galaxies that are doing that. And because this galaxy is lensed, we can really study it in great detail. And in fact, the plot here is just to show that we measured that escape fraction varies spatially, and we think that's due to different gas along the intergalactic, in the intergalactic medium along the line of sight. So this is a really great, this is a fantastic target. We have obtained narrowband imaging with Hubble that we are working on right now. And so we've mapped out where the Lyman alpha is. It's at a redshift such that you can get narrowband imaging of Lyman alpha, H beta, and the UV continuum. And so we can make these funky narrowband images of where the ionized gas is escaping and where it's being excited. And so what's really striking, and these are from some papers in preparation, is that right here is there in what's marked F is Karen's reconstruction of what this galaxy looks like in the source plane. And here's this ionized, this is the ionizing source that's producing the ionized photons and then has this big bubble of H beta around it, of ionized gas around it. And it looks for the world like HARO 11, which is the nearest example of a galaxy that is leaking ionizing photons. So we really can try to do a apples to apples comparison between an ionizing galaxy in the local universe and an ionizing galaxy out at redshift 2.4.
And can I ask a quick question about this before you move on?
Yeah, sure.
So you said on the previous slide that you interpreted the variation in the inferred escape fraction as structure in the IGN. Could it not be local as well and be telling you something about the covering fraction of gas in the galaxies, or is there something else that leads you to believe
it could? I have to go back to the 2017 paper and see how we convinced I have to go back to the paper and see how we convinced ourselves of that. I think it has to do with, because it's the same region, it's the angles that you're seeing of the gas, right? You're seeing the gas right in front of the ionizing source. And even among the different lensing paths, it's still the same. It's like a plane parallel of gas.
Okay, so the different lensing paths aren't so great.
They're not different enough.
Okay.
Yeah, because you're in the near field. Yeah.
Sure. Thanks.
Happily, we put in a proposal led by Emil with Webb to study this galaxy with the IFUs with JWST, and that was successful. So we'll be getting more data on this really, I think, important source to show us how ionizing photons escape from galaxies. Okay, I want to talk a little bit about massive stars, which has been something I've been geeking out a lot over the last couple years. Certainly, the ionizing spectrum of a galaxy is very sensitive to its stellar age and metallicity. You can see here, these are just some Starburst 99 models. As a simple stellar population ages, the number of photons that can ionize hydrogen here at 900 angstroms and helium at 500 angstroms drops really quickly, right? It's only the most massive stars that are able to do that work. And that's not just, you know, releasing ionizing photons, that's also powering all the nebular gas, all the H alpha, H beta, O3, all of the nebular lines are powered by this stuff. And it's also what's driving the outflows. So these massive stars are super important to the spectra that we see, and they're also super important in evolving the galaxies, both in terms of driving winds and creating heavy elements. They're really a pain to study. So we, in a paper by John Chisholm, 2019, we analyzed the Megasaurus data, and you showed how we can measure the age and metallicity of these stellar populations. And there are currently big uncertainties in the massive stellar populations from a theoretical standpoint that have to do with how important are binary stars. Here in the yellow and red color scheme are stellar populations that have binary stars. And then in blue are ones that, in dark blue is one that does not. And you can see factors of up to 3 in how much ionizing photons you make for almost the same non-ionizing UV spectrum. Right, so and this really matters if we don't know within a factor of 3 how many ionizing photons a galaxy can make or stellar population makes. And so in this paper we looked at, and so, you know, I think it's a thing that we're investigating right now is trying to close the loop between the ionizing continuum that we can't measure, the non-ionizing UV continuum that tells us about the ionizing continuum, and then the nebular lines that are responding to the ionized, you know, they're in ionized gas, they're responding to the ionizing continuum. So we're trying to close that loop, which is at some level going back to your copy of Osterbrock or Ferlin and Osterbrock, but has never been done in either the nearby or the distant universe. So we're trying to use that to understand what the stellar populations of these galaxies really are. This is in John's paper. We work out at length a number of diagnostics that are unique, that are sensitive to age and metallicity in very different amounts, such that we can simultaneously constrain both. So we're able to measure the stellar metallicity of the integrated population. And this is from blue UV, rest frame UV light. So it's the age of the youngest stars and the metallicities of the youngest stars. And then compare that to the nebular metallicity, and we get kind of shockingly good agreement. So we're arguing that we really can measure the oxygen abundance from the stellar light. We also see the trends that we expect to see between the ages that we infer of the stellar populations and things like how bright the equivalent widths of strong emission lines are. I'm going to skip this for time. Okay, so I'm going to talk a little bit about gas outflows and then get a little bit to the future. What we've done, so there's beautiful data on the outflows in the Megasaurus spectra. What we've done so far is analyze the stacks between redshift 0 and redshift 2. That's what's shown here, and find that they're really, the velocity profiles are really similar. And so we speculate that that means that, you know, the outflows are, the processes that are governing the outflows are, you know, maybe universal, at least between redshift 0 and redshift 2. What we haven't done yet, and is work that we're slowly working through, is to not use stacks here, but do individual galaxies and look at the outflows galaxy by galaxy and relate that to the galaxy properties. And so that's work in progress. We also, you can see in the Megasaurus spectra some signatures of very hot gas. You get oxygen 6 in absorption, which is coming from 10 to the 7 Kelvin gas flowing out of the galaxy at hundreds of kilometers per second. And so that's part of the really hot wind that's coming out of these galaxies. And we see that ubiquitously in our sample. Speaking of winds, in the sunburst arc, we see very strong winds. And in fact, we see that in blue here is the leaker. That's that little knot that's seen 11 times. Comparing it to the rest of the galaxy, the leaker has much stronger winds with a very broad, you know, this broad component is much, the broad component is much stronger. And you can also see just how dramatically different are the stellar populations, right? The leaker has strong nitrogen 5 and strong carbon 4, which are all signatures of very young stars. All right, I want to do one more science topic and then talk a little bit about the future. This is one that was accidental, but it is nifty. There's a whole field of quasar absorption line spectroscopy in which people look at absorption lines of, that are in the spectra of distant quasars, but they have nothing to do with the quasar. They're just gas in the middle. And so you're using the quasar as this lighthouse to probe the nature of all the gas between you and the quasar. The problem is that for quasar absorption line spectroscopy, your background target is a point source. So you don't have any idea. You can get a column density, how much gas is along the line of sight this way, but you have no estimate of how big the features that you're looking at are. Are you looking at little gas clumps? Or are you looking at a whole galaxy? If you do that same technique of quasar absorption line spectroscopy, but use a galaxy as a lens galaxy as your background source, then you have a lot more room to work with, right? You get an absorption line profile in every spatial resolution element of your background source. And so this was this is a technique pioneered by our collaborator Sebastian Lopez in his Nature paper, arguing that we can use this to understand in the X and Y, right, of these absorbers, of understanding their spatial extent and their distance, and how, especially if you know what the absorber is, in this case, that's the absorbing galaxy, and then you see the effects of gas all along this arc. That you can understand how far out these winds flow from the luminous galactic counterpart. So that was a surprise to me that has been really useful to that community. And so I'm working on a paper in preparation that just summarizes all of the intervening absorbers that we know of in the Megasaurus sample so that people can do this kind of tomography. We've written a bunch of papers. I've talked about several of them. So really trying to get as much as we can out of the Megasaurus spectra. All the spectra are public. I should have said that earlier on. I wanted this to be a public resource and not like, our own little secrets. So electronic versions of the spectra were published in the sample paper back in 2018, as well as our best fits for all to the stellar populations. And I'm I talked about some of these. Let me just skip ahead to what have we learned, and then a little bit about Webb, and then I'm going to make sure I have time to take questions. So impact, what have we learned? We have demonstrated techniques to measure the metallicity and the ages of young stellar populations out at redshifts of 2 to 3, and shown that those are quite robust. We get the same metallicity for stars and gas, which is quite different from some results in the literature that argue that those are very out of bed with each other, and we show why we think that is. That's in the Chisholm et al. Paper. We are able to infer the ionizing flux from the non-ionizing UV and plausible theoretical uncertainties. Binarities, rotation, and stellar and star formation history can change the ionizing flux by factors of 10. And so we really should be able to constrain what the massive output is, the massive star's output is from these measurements. We've detected escaping ionizing photons from star-forming regions, and we use that to test some indirect indicators of escape likelihood. We're also building up samples that are as good as we'll ever do of understanding how, at the best spatial resolution that anyone has yet done at any redshift, to understand how ionizing photons escape galaxies. We've tested a bunch of new diagnostics for use at high redshift. We hated a lot of them, unfortunately. That was in that set of diagnostic papers. A lot of them just didn't work out, but you got to try. And so we now know we have then recommended diagnostics that we think that should be reliable for use by Webb at high redshift. With some caveats that if you don't think about, if you're mixing and matching diagnostics, you can see redshift evolution that is just using different diagnostics. And then we're working on understanding the outflows of these galaxies and linking them back to the properties of the host galaxies. Looking ahead to Webb, and I can happy to take any Webb questions that you want. That's my programmatic job, is project scientist for Webb. So I am also, in my science time, the principal investigator of this early release program called Templates, which is just throwing all of the JWST observing modes that seemed useful at 4 very bright lens galaxies to characterize how well spectroscopy and imaging is working with Webb as soon as possible. And so these ERS programs are public. We see the data at the same time the community does, and we're on the hook to deliver a bunch of high-level data products to the community, as well as a bunch of cookbooks showing what we tried, whether it worked, and what our recommended best practices are to try to get the community up to speed as fast as possible in doing spectroscopy my intent was that you shouldn't have to care about lens galaxies, you should just care about spectroscopy, and there's just signal to noise to burn here, and a large large dynamic range in surface brightness, and so we can really try to understand what are the best practices for doing this kind of work. Maybe I should just stop there and so we have time to take questions.
Okay, great. Thanks very much for that. Really great talk. So it looks like, Robert, you have a question from the chat posted just a few minutes ago. Do you want to unmute?
Yes. So when you were talking about the outflow, do you actually know what causes the outflow?
Do we understand what causes galaxy outflows? There can be multiple causes. Galaxies with active galactic nuclei can have strong outflows. Galaxies that have recently formed stars can have strong outflows, as well as post-star bursts, where you still see the outflow, even though the star formation was a couple 100 million years in the past. For the star formation, it is some combination of it's feedback, but now we're going to get into what is the feedback actually. What are the relative contributions of the stellar wind, the supernovae, and how important, for example, is radiation pressure on the dust and driving it out versus kinetic versus gas processes blowing out the gas. So I would say that the simple answer is sure, it's either star formation or AGN. And then this next more difficult question is it's really complicated and there's a lot we don't understand.
Great. Daryl, go ahead.
Hi, Jane.
And and then I should say, hi, Daryl. Okay, go.
So I think I just wanted to follow up on Robert's question. This is one of those like annoying other wind questions. How can you tell it's an outflow and not an inflow? Isn't this just notoriously difficult to piece out?
Let's go grab a spectrum. Let's see. So for this one, so this is an emission of an optically thin line, right? So, and you can see, well, I don't know if you can see from the plot, but you can, for the leaker here, so there's a broad component, so it's going out in all directions, and it's biased toward you. So it's biased toward negative velocity, so coming at you. And if you look at the absorption lines, yes. So the black vertical lines here are the systemic redshifts. And because this is an absorption, there's an emitter, and then there's the front half of the galaxy facing you. And because it's absorption, it has to be coming at you, or it's going in the wrong direction and you don't detect it. So it's coming at you, and it's really blue shifted.
Okay, so you really benefit from being able to see the galaxy and using it as your reference, and then you know which is in front of it and which is behind it. Okay, thanks.
Yep.
I'm going to call on myself for the next question or two. I was thinking about this Bayless et al. Result, the X-ray follow-up, and I was wondering, first of all, just how much Chandra time did that take, and is that the kind of thing we can look forward to seeing more of? Because studying, for example, like the X-ray luminosity to star formation rate relation at very high redshift could be really interesting for a lot of reasons.
So this wasn't that long. I'm trying to remember this is the Phoenix arc. It's a couple 100 kiloseconds. So it's not chump change, but it's not super, super deep. And if I was sharper on the draw, I could work it out from this plot. We put on the links line here of what a next generation X-ray facility could do without lensing, to make the point that this is what you could do either with with a future facility routinely for unlensed, just field galaxies. There's a couple of these that we're getting Chandra for at the 100 kilosecond level. So I think we're going to be able to repeat this at 3 galaxies total, including this one.
Cool. And my second question is about globular clusters. So when you have these super high resolution reconstructions, are any of these clumps consistent with clusters as massive as present day globular clusters? This
is the point where the colloquium where I beg someone who really understands globular cluster formation to tell me whether these are globular clusters in formation, because the redshift is about right. These are redshifts 2 to 3. They're small. The sizes in this paper, the radii are 20 to 30 parsecs. We don't have any velocity information, so I don't know if they're bound, right? Because the velocity dispersion of a globular cluster is tiny because they don't need dark matter. But we can't measure that. This is all imaging. And in fact, a proposal that I put in that got rejected for Webb was to do Webb spectroscopy of this guy and measure velocities, because you should be able, it's high, we convinced ourselves it was a reasonably good measurement to try to get velocity, get rotation curves for this thing of just, get a velocity for every one of these things and see how is it rotating, and then do something about, is it bound or not? What's the, it's hard because the spectrographs on Webb are only R with 3000. They're not really high spectral resolution, but you can do it. So I think there is an unsolved question about how, certainly when we look at lens galaxies, we see clumps. They are clumpy. The distant universe is clumpy. We see a lot of clumps that are on tens of parsec scales. And is this how you make globular clusters? I don't know.
We'll have to have you back after the next cycle when that's accepted. Okay, we're reaching the end of the hour here, but we have time for maybe one more question if somebody has one.
Can I ask sort of a slightly non-science question, Jane?
Sure.
How are you all feeling about the James Webb launch? Are we jazzed? Should we all be jazzed? Are we terrified?
Yes. I mean, it's real.
Pirates.
Oh, okay.
Pirates, Jane, the pirates.
Oh my God, that is so not on the project managers. I was in the room when the project manager was complaining about, that's my real problem is pirates. How are we feeling? So it's going really well. The telescope is, we did all the vibe and acoustics. So we hit it with 140 decibels of noise. We shook it harder than the rocket will. We then tested that the thing still deploys, that the sun shield comes out and the mirrors come out after all that shaking and all that shaking. We are now in the process of folding it up. So that final fold is most of the way done, which means we're not unfold. This is I think this is folding up the parachute before we jump out of the plane here. Oh, sorry, I'll get to Vicky's question in a. So, we're folding up this origami telescope for the last time, and it's got to come out in space with no assistance. And so that process is almost done. The pirate thing comes in. So we're really, really close. This is getting really real. The only stages that are left at this point is that we have to finish a little bit of that packing. There's a couple electronics boxes that we're not happy with. We're going to swap out for the radios. And then we are going to put it in a shipping container and ship it on a custom roll-on, roll-off ship that's used, that's owned by Arianespace to move the rockets down to French Guiana. And we're going to put it in that ship and we're going to send it through the Panama Canal from Los Angeles to French Guiana. And somebody who was, so the pirates thing was that someone at a newspaper or a magazine who was really bored and thought she could write a story was like, what if Webb gets attacked by pirates? And asked scientists, not engineers, but scientists, if they were worried about pirates. I'm not worried about pirates. The United States knows how to keep ships safe. We have a Navy. It's not that hard. But the thing that is, so I would say that how are we feeling is that stuff is getting real. Like we are really, we are on track for a launch late this year. There's just not that much more that has to happen. We have to put it in the box. We have to put the box on a ship. We have to send it out to French Guiana. And then there's some work that needs to happen at the launch pad, but it's not a lot. It's things like fill the gas tank, fill the oxidizer tank, do some final checks where we check that the radios on board the spacecraft will talk to Mission Control in Baltimore and that we can send it commands. So just double checking all of that. Things like, could you, wiggle your mirrors a little bit? Do they wiggle? Great. Okay, turn on this power box. Did it turn on? Great. Just, all of that functional testing. And then they count down in French and it goes up. So I think we're feeling that it keeps getting realer and realer. And we're doing a lot of launch rehearsals. My summer is I get to take a brief vacation and then we rehearse launching over and over, basically. And we rehearse using the, commissioning, and we rehearse using the science instruments. And so, that's a team, especially for all the 4 science instruments, a multinational team that is doing fantastic work despite COVID to get this thing up. So yeah, that's how we're feeling, is that we're going to really have a Webb telescope. And then the terror is that, it's got to deploy correctly in space. And I mean, at some level, you build a 6.5 meter telescope that fits in a 4 meter fairing, it's going to have to deploy. So this is going to be a problem we're going to have for every new space telescope. So, it's got to deploy.
All right, well, I think that's a great note to end on. So thanks again, Jane, for joining us virtually today. That was a great talk. Really enjoyed it. So for everyone else on the call, please share your appreciation for Jane's talk in the chat before you leave. And we hope to see you in Montreal in person sometime soon.
Indeed.